Assalamu alaikum. In part 4, we talked about reliability and promised you to explain its opposite term, risk of failure, through an example of steel pipe brittle sulfide stress cracking failure in a sour service. But before we talk about such risk of SSC failure and explain risk in general, which is the main topic of this part, and since I promise you to explain such a specific metallurgical failure risk in oil and gas industry, let me first try to explain some metallurgical terms. So, what is brittle failure? What is sulfide stress cracking failure? And what is sour service? Well, failures in most engineering steels can be either a ductile fracture where material yield means deform, strain first in the direction of the applied stress before complete breakage, which will give a clear warning sign of plastic permanent deformation, like pipe bulging during a hydro test or steel bridge bending due to excess loads before a complete rupture or failure take place, and which will only happen after exceeding the ultimate tensile strength of the material, resulting in material complete failure as expressed in the famous engineering stress strain curve, where the area under the curve of the plastic deformation part represents the energy absorbed by the material before failure, or what is called toughness, and which is an important property of material when we talk about brittle fracture, since brittle materials absorb least energy before failure or fracture, and the mechanism of brittle fracture is always associated with sudden breakage and fracture at lower stress level than normal ones, and this sudden nature of the failure without any visible warning signs of deformation is resulting in losing the chance to do any preventive actions to avoid the failure and its catastrophic consequences. And just to know the impact of brittle fractures, we need to know that in 2007 in China only, 257 cases of accidents of special equipment occurred, which caused 325 deaths and 285 injuries, and more than half of these accidents were caused by brittle fracture. But what can make material fail in such a brittle mood? Well, some causes can be that material itself is having problems, like high sulfur, high phosphorus levels, and might have high oxides levels, like in some old steels that were semi-killed steels, which means not fully deoxidized to remove such oxides. And the most famous disaster took place with a brittle fracture due to this type of steel, in combination with low temperature and application of impact load, is the famous 46,000-ton Titanic steamship that had the disaster in 1912, with 2,227 passengers and crew aboard, where the complete brittle fracture took place in the hull of the ship after striking at high speed the iceberg with its side. It was after this collision the disaster started, and where the very low water temperature increased the steel brittleness. Since all steels generally exhibit a transition from ductile to brittle behavior at certain low temperature, DBTT, where fracture behavior follows sudden cleavage mood. While for modern fine-grained tough steels, DBTT, ductile brittle transformation temperature, go down up to minus 100 degrees centigrade. But what is fine-grained steel and why it is tough steel, which can resist cracking and failure at such low temperature and impact load? Well, in order to answer this question, I need to give a brief and general explanation of some physical metallurgy basics. I apologize for the complexity that this can generate for non-metallurgists. I'll try to simplify as much as possible. Well, steel is mainly an alloy of iron and carbon, and when it solidifies or crystallizes, its atoms arrange themselves in a unique symmetrical crystalline structure, BCC body-centered cubic or FCC face-centered cubic, which reference as steel allotropic form. And when these crystals start nucleation and growth, during solidification, crystallization, building their repeated symmetrical unit cells, or what is called lattice, growing in all directions, then different growing lattices interfaces will meet, developing a border separating different growing lattices and stopping further growth. So those crystallized lattices are grains, and the separating borders between them are grain boundaries. And since they were stopped against certain growing force inertia, they are usually stronger than grains and characterized with high stored energy. That reduces the brittle fracture probability through resisting dislocations movement and cracks propagation at low and normal temperature. So, usually the brittle fracture is taking place in the brittle materials by fine crack propagation through the grains itself, or what is called transgranular cracking, and is taking place suddenly and rapidly through separation across well-defined crystallographic planes. However, if the grain boundaries are weakened, like in case of working above certain high temperature called creep temperature, or in case of embrittlement of these grains boundaries by hydrogen in certain sour service conditions, the alternative fracture propagation path will follow the grain boundaries, and this is called intergranular fracture, and this is a typical mechanism of sulfide stress cracking failure. But how can we evaluate the risk that a high-strength low-alloy steel pipe will fail with the SSC mechanism in a sour service condition? And what is actually meant by sour service? Now, sour service generally is a wet hydrogen sulfide containing environments. NACE standards define sour environment as fluids containing water as a liquid and hydrogen sulfide at a partial pressure above 0.05 psi. And that may cause sulfide stress cracking of some steels. And from health hazard and risk point of view, we shall know that H2S gas is a highly toxic gas and can be fatal at certain exposure levels. H2S is also very detrimental to high-strength steels and can cause initiation of cracks at steel surface through mainly hydrogen embrittlement mechanism when exists in certain humid hydrogen sulfide environment, especially if combined with certain stress loads, and this is why it is called sulfide stress cracking. SSC is a catastrophic failure as it results in a brittle fracture, and it can occur at stresses falling within the range of typical design stress. And as per the standards covering these types of services like NACE, MR 175 and ISO 15156 standards, a cracking of metal in SSC is involving corrosion and tensile stress, residual and or applied, in the presence of water and H2S. Note that SSC is a form of a hydrogen stress cracking, HSC, and involves embrittlement of the metal by atomic hydrogen that is produced by acid corrosion on the metal surface promoted by presence of sulfides. The atomic hydrogen can diffuse into the metal, reduce ductility and increase susceptibility to cracking, especially in high-strength metalling materials. Now, and after this quite complex part, let's try to apply what we learned in the last part about reliability. So in order to reduce the risk of failure by SSC, manufacturer can reduce the probability by increasing product engineering reliability as per the following. First, and since high-strength steels are more susceptible to SSC than low-strength steels, it is a common industry standard to limit the hardness of these types of steels to 250 Vickers hardness. Then, microalloying these steels with molybdenum and vanadium, increasing tempering temperature to improve the morphology of steel, grain size, shape and structure. Steel surface shall be free from defects or stress risers. And now how to reduce the risk of failure from service point of view by the end user. We should know that the severity of SSC decreases as the temperature increase, pH level increase, less acidity, H2S concentration decrease, service stress levels decrease. But since most of these conditions are somehow difficult to be controlled when we actually run a production tubing downhole into a sour oil well with certain H2S pressures and under certain tension stress levels. So, the client or end user main responsibility is to do the correct selection of steel for the right service severity level or region, or reduce the severity if possible. Finally, and after this relatively detailed and zoom-in explanation of the possible causes for such specific failure risk and the ways to prevent it from manufacturer side and from client end user side, reliability, let us now zoom out and try to see the whole picture of almost everything we learned so far. By looking at one example from one international standard, which is American Petroleum Institute Standard, API 5CT standard, which is a standard covering manufacturing of steel pipes used in such oil and gas upstream services, And let us take the example of one steel grade which is intended to be used as per this standard in sour service, and how that API standard made it very clear for the end user, the purchaser of these sour pipes, that it is their responsibility to make sure that they are selecting the right product grade for the right sour service severity level, and that the manufacturer full and consistent compliance with this standard does not guarantee the reliability of this grade in such specific severe sour conditions. Well, let's read this quoted clause 5.1 together and focus carefully on the underlined part. So, particular attention should be given to the application of grade C110 in NACE MRO 175, ISO 15156-1-2, SSC regions 2 or 3, as this material is not suitable for all sour hydrogen sulfide containing service conditions. Note, the SSC test is for quality control purposes only and does not qualify the material for any specific sour service application. It is the product user's responsibility to ensure that the product is suitable for the intended application. And we can see in this graph quoted from ISO 15156-2 standard, the SSC regions 2 and 3 that were mentioned in the previous quoted clause from API 5CT standard. So, regions 2 and 3 are characterized with higher H2S partial pressure combined with lower pH values, higher acidity. So, as you can see, this example summarizes almost everything that we have learned about definition of quality as fitness for service, consistency, and the importance of continuous improvement to achieve reliability, and the combined responsibility of manufacturer and end user to achieve that, especially when we deal with risks. And this is what we will learn in this part, which is just started.